Welcome. Good morning, good afternoon, and good evening, depending upon where you're dialing in from. I will be your moderator today. I am a senior research analyst with BlueTech Research, and today we're doing the next webinar in the BlueTech webinar series done in partnership with InfoCast on zero liquid discharge. So today we'll be talking about the very exciting area of brine concentrate management and the market dynamics and technology trends in that space. Just to let you know, the slides will be made available, and the format of today's webinar will be 45 minutes of presentations, followed by a 45-minute question and answer period where the questions you type in, I'll be directing towards our panel. Our next BlueTech webinar to be held on February 21st will cover the water and wastewater issues within the oil sands. And so I hope some of you will be joining us for that. Just to give you a bit of background about who we are, BlueTech Research is an O2 environmental company. We're an independent market intelligence and advisory firm focused exclusively on the water technology industry, looking at what are the innovations happening within there. And we're the premier source of actionable market intelligence for making strategic decisions in that space. The webinars are one element of the BlueTech Research Advisory Service. There are several others that our clients use, our subscribers use to identify and assess water companies and technologies they might be interested in investing in, acquiring in, partnering with, looking to understand new water technology market opportunities, identify areas for growth, as well as look at identifying patent trends and opportunities for licensing technologies. If you'd like to learn more about these services, please go and visit us at bluetechresearch.com. Now, for today's panel on zero liquid discharge, we have an all-star panel, including Dr. Michael Mickley from Mickley & Associates, Dan Bjorklund with Aquatech International, and Bill Shaw with HPB. I'm going to give a fuller introduction right before each of their presentations to give you a bit more information about who they are and what they've been involved with. To just start with some opening remarks, zero liquid discharge is a term that can be defined in several different ways, and Mike's going to give us an overview of what the literature says on this. It's a goal, ultimately, of not having waste leave a site. It's one way of defining it, but it's often used interchangeably with a set of technologies that usually includes an evaporator and a crystallizer. But the idea here is to recover the maximum amount of water possible and avoid having to deal with a liquid waste effluent, preferably having a solid waste to get rid of. Types of industries we're going to looking at for this include power plants, oil and gas, and other industrial applications. And we're going to hear an overview of those from Dan. But there are other ones, and we'll be looking at some of those alternative areas in the discussion and answer period. At BlueTech Research, as I mentioned, one of the things we're looking at is tracking innovation, and we've got some of the major zero liquid discharge technology providers here speaking with us today. We're also looking at some of the other companies that are smaller startups with innovative technologies. I've given you a sample here of ones that we have in our innovation tracker. That's one of the elements of the BlueTech Research service. Memsys, definitely a hot topic company at the recent Singapore International Water Week. They've got a zero liquid discharge technology with their vacuum multi-effect membrane distillation. As the name implies, it's a membrane distillation technology that uses multiple effects and driven by a vacuum to achieve really high rates of water recovery. Saltworks in Canada have the Salt Maker technology, which is a humidification, dehumidification technology aimed at zero liquid discharge. There's geoprocessors out of Australia primarily that have a SalProc process for selective salt recovery and crystallization. We're tracking New Logic with their VSET membranes, which are use a vibratory shear mechanism to reduce fouling, and therefore it's a higher recovery rate. Maybe not a zero liquid discharge technology in its own right, but to be used in conjunction with other technologies to achieve ZLD. and Plus Technologies out of Germany with their distillation technology that can be used to recover purified salt, gypsum, and magnesium hydroxide precipitation. These are just some of the companies that we're tracking that are some of the more early stage companies in the ZLD space. Of course, there's the bigger companies like Aquatech and HBD, who will be speaking today about their evaporators and crystallizers, and Bill's going to tell us a bit about the cold process with HBD, sort of an innovative take on some of the conventional evaporating crystallizer technology. Also, some of the other major companies like GE and Siemens have their own, including a non-thermal desalination technology that GE has. And whether or not ZLD is exclusively thermal technologies is one of the things we'll be looking at today. Another thing that we do at Blue Tech Research is often do a patent analysis. Zero liquid discharge is a difficult area to analyze for patents because evaporation and crystallization, which are, of course, the dominant technologies in this space, are fairly generic terms, so it's hard to filter down to specifically patents looking just at this particular goal. But if we do a search looking for the term zero liquid discharge, you can see within the top assignees, the top 1, 2, 3, 4, 5, 6, that those names, HBD, Aquatech are up there, General Electric with GE Ionics as well, and just Ionics on its own, but also the University of Southern Carolina and Heartland Technologies, which is an oil and gas related company, are some of the major companies filing a lot of patents that include the term zero liquid discharge. So there's a lot happening in this space. It's a really interesting one. It was one of the major buzz topics at the recent Singapore International Water Week, as I mentioned, and I'm looking forward to hearing the panelists speak to it. I just had a quick question here come in. Will an electronic copy of the presentations be made available? Yes, it will. So with that out of the way, I'm going to introduce Dr. Mike Mickley. He's going to kick off our presentations today. Dr. Mickley is an internationally recognized expert in brine concentrate management and is on the editorial board of Desalination and Water Treatment. He's been working in this desalination field since 1966, and since 1990 has been really focused on the area of concentrate and brine management. So he's going to bring an interesting perspective to the webinar, having involved with site-specific evaluations of disposal options as a consultant to major engineering companies, with recent work looking at salt recovery in places like Oman, the UAE, and South Africa. And he's been involved with research projects funded by a whole raft of organizations, including the Water Research Foundation, Bureau of Reclamation, Office of Naval Research, Water Reuse Research Foundation, all of the projects looking at concentrate and brine. Some of the most recent reports include a WRRF report entitled Survey of ZLD and Volume Minimization Technologies for Water Utilities, and a 2013 report with the WRRF on development of a knowledge base for desalination, concentrate, and salt management. So Mike was going to be giving us an overview of the subject of ZLD, including the tricky task of just defining it, and he'll also be giving us an overview of drivers, ZLD characteristics, and areas of research. So go ahead, Mike. You can unmute yourself and start your presentation.
Tyler, thank you. I want to start by talking about that there are different definitions of ZLD in the literature. I have just a bit trouble advancing the slides. Let me get familiar with that. The original definition has to do with no liquid waste being transported across the plant boundary. In the literature, however, sometimes ZLD refers to processing wastewater to solids. Sometimes it refers to the use of using thermal evaporative equipment in high recovery processes. Zero liquid discharge does not necessarily involve thermal evaporative processing, but most frequently does. And a very typical processing scheme is the one shown here, involving perhaps a pretreatment step followed by a reverse osmosis step, and then a thermal brine concentrator, a thermal crystallizer, or a spray dryer, or taking the brine from the brine concentrator directly to an evaporation pond. Today we will be using the original definition for ZLD. There may be exceptions mentioned periodically. So we have a wastewater and we want to dispose of it. The options for that are listed here, and there are subcategories to these, but these are the broad options. We might discharge wastewater to a surface water. We might discharge it to a wastewater treatment plant. We might deep well inject it. We might send it to a land application, which involves percolation ponds, infiltration basins, or using the wastewater for irrigation. We might send the water to an evaporation pond. In the case of solids, solids might go to a landfill. Now, those are disposal options. There also are some wastewater management options. We might look for a beneficial use. Unfortunately, beneficial uses are rarely found. Many of them are unproven, and most of them are not a final fate situation for the wastewater, meaning that after beneficial use, there may still be disposal issues. Another water management possibility is further treatment of the wastewater, and of course, this gets us into the high recovery, including ZLD processing. And as part of this ZLD processing, we might recover salts and other byproducts. Now, so we have a wastewater, and we're thinking of treating it further. And at any step in this process, we might consider, can we dispose of it, or can we obtain byproducts? Can we make use of it? And as you see, moving from left to right, we're pushing towards zero liquid discharge. And the question comes, what drives us to indeed pushing us all the way to considering zero liquid discharge? And I've got 3 slides talking about drivers. There's a considerable overlap between them, but they're from slightly different perspectives. On this slide, one of the drivers for ZLD is simply that we have difficulty in implementing the conventional disposal options. One reason is that there are increasing regulations and permitting requirements associated with those disposal options. Another reason is in many locations there's a lack of available disposal options. There's also increasing costs associated with disposal options. Another category of drivers has to do with the growing environmental and resource concerns. Water, or high-quality water, is, of course, a scarce resource, and with a growing population, there's need to be considerations for other resources, and processing of lower quality waters, including ZLD processing, is a solution to that. ZLD is also driven by environmental issues and also public perceptions. So whether those perceptions are correct or not, the public perceptions affect decisions. Now, looking at drivers from another perspective, again, we have regulatory drivers, regulations tightening up. We also find over the globe there are, unfortunately, many lawsuits having to do with situations where groundwater has been contaminated. And frequently, the mediation that's called for involves high recovery or ZLD processing. Many times it's easier to get a ZLD permit as opposed to a permit for the various disposal options. There are economic drivers. Industries are increasingly realizing the benefits from water reuse. Again, there are environmental concerns driving a push towards ZLD. We can reduce the environmental footprint with ZLD processing. Many companies are mandating look at high recovery processing. We can reduce risks and liabilities associated with transporting of chemicals and products, particularly in a situation where we might incorporate salt recovery with ZLD processing, use that salt either directly or as a precursor to making other chemicals that might be used in the process. There's a growing general social responsibility surrounding reuse. And again, the public perception plays an important role. And unfortunately, the public's consideration of industrial wastes include the terms toxic and hazardous. And most wastes are lumped under those headings in the minds of the public. Another driver is resource conservation. There's a concern for both the quantity and quality of the water supply. The water produced by thermal technologies is very high quality. Final driver is the push towards what I call sustainability. What I mean here is this push, in part, is driven by the necessity for to respond to the scale of many social, cultural, economic, environmental challenges that we face. But perhaps more importantly, it's also driven by the realization that short-term thinking can be and usually is detrimental, and that sustainable practices can be profitable in the short term. The next slide gets into this point in a little greater fashion. This slide might better be entitled Drivers for Wastewater Management. You see a time arrow moving from left to right. In the past, wastewater management really was disposing of the wastewater, and the drivers were regulatory. In more recent times, more attention has been paid to managing wastewater, with the realization that there are economic, environmental, corporate, and operational benefits from doing this. And then even more recently, we see the increased use of the term sustainability. Now, the three bullet items below, I want to make the point that when we apply ZLD, environmental risks do not go away. And in some of the newer applications, such as working with unconventional gas-produced waters, the complexity of the wastewaters are different from the historical wastewaters that the ZLD has usually been applied to. These are nastier waters, so there are greater environmental concerns. The real reason for pointing this out is I've interacted with a number of smaller companies, and I see them, many startup companies, taking let's say a longer-term view of what makes sense in treating wastewater. It seems that all of them are considering ZLD or near ZLD processing, and many are considering the longer-term sustainability issues, including recovery of byproducts and or use of some of the products in other parts of even the ZLD treatment process. I think such approaches are needed to address wastewater treatment in a more sustainable and long-term context. Now, moving from drivers to characteristics, well, I guess first some trends that I've noticed. Growing number of drivers for ZLD, growing number of applications, a growing interest in searching out the synergies from looking at water, energy, and resource issues, growing mention and concern with sustainability, growing interest in recovering salts, growing interest in linking the processes with renewables, and certainly a growing amount of research. Now, moving on to characteristics of ZLD processing, we've already bumped up against the first two bullet items, the type of technologies that are used in a typical processing sequence. As Tyler mentioned, there are three main suppliers of the large systems, and we're fortunate to have representatives from two of those. There are many new companies, as I've mentioned, focused on newer applications and seemingly taking a longer-term view at wastewater treatment. Different from those bullet items, in my work as a consultant and doing feasibility studies for different groups, I find that it's very challenging to estimate performance and cost of the thermoevaporative equipment. And there are a couple of reasons for this. One, as mentioned, there are few equipment manufacturers, and the design practices are fairly closely held. But perhaps the biggest reason is there's a complex dependence of performance and cost on water quality. And unlike for reverse osmosis systems, where we have software available to predict performance and cost, there are no such software available for the predicting thermal process performance and cost. And then, of course, we introduced the complication of dealing with temperature as well as water quality. The next four bullet items, I want to expand upon the point of the difficulty of estimating performance and cost. You see in this first bulleted item listing of a number of salts ranging at the top from low solubility to high solubility as we go down. Now, the concern about solubility of salts is as we concentrate a wastewater, we push up against solubility limits, and we may force some salts to come out of solution and scale the membrane or scale the heat transfer surfaces. The top three salts listed here, calcium carbonate, calcium sulfate, and silica, are issues for reverse osmosis processing along with other salts. But when you get into even greater levels of concentration, as we do in thermal equipment, other salts come into consideration. Many times the double salt conglomerate, which is a sodium calcium sulfate salt, is the limiting aspect or limits the performance of thermal equipment. If it doesn't limit performance, many times the limitation is due to sodium chloride or sodium sulfate or some other salts. The point here is that water quality issues are much more complex than what we deal with when we talk about reverse osmosis. There are other, in the bottom bullet item, there are other possible limiting performance issues, including boiling point elevations, the level of suspended solids, occurrence of foaming, and these also are related to the water quality. Now, in 2008, I produced a report for looking at these challenges and influence of water quality on performance and cost. And we devised 7 different feed compositions that corresponded to real concentrates. We normalized the concentrations, the total dissolved solids, to 8,000 parts per million to eliminate salinity as a variable. And we wanted to find out how far a brine concentrator could concentrate these different waters. And because of the difficulty of estimating performance, we engaged one of the 3 major equipment manufacturers to use their in-house experiments and software predictive capabilities. And the results were, for one of those waters, it could be concentrated only to 160,000 parts per million. For another water, it could be concentrated all the way to 358,000 parts per million. And so the point of this bullet is, I guess it illustrates that it's difficult for somebody outside of the major companies to estimate performance, but also reflects that the strong dependence of performance on water quality. Now, that bullet below that, also in the same study, we looked at 5 commercially used ZLD processing sequences that involved all the steps involved reverse osmosis, brine concentrators, crystallizers, or evaporation ponds, different sequences of those. And we looked at what the cost would be involved in treating the 7 different waters. So there are 35 different simulations done. And the capital cost, the highest capital cost was twice the lowest capital cost encountered. But even more significant, the highest operating cost was a factor of 7 higher than the lowest operating cost. The capital cost did not correlate with the operating cost. And the most cost-effective treatment scheme was not the same for all these 7 waters. So this points out again the strong dependency of cost on water quality and the difficulty of predicting what would happen based on let's say, one site-specific study. It's risky to generalize both on performance and cost based on one study. So moving on and finish up with the characteristics, we get into the, I think I skipped ahead too far. Here we go. High capital costs and high operating costs associated with the thermal equipment. It's just based on their nature. And to give a relative idea, I've contrasted those costs with those having to do with reverse osmosis. So in the first bulleted item, we talk about unit capital costs in terms of dollars per million gallons per day treatment. And we see a range from brackish water, RO, of a unit of 2, all the way up in terms to a thermal crystallizer of a value of perhaps 30. And these are representative values. They, of course, differ from site-specific situations. When we talk about operating costs, usually the operating costs are dominated even above 90% perhaps with the energy issue. And you see listed here numbers for kilowatt hours per 1,000 gallons of product, ranging in the case of brackish RO from a value of 4 all the way up to crystallizer for a high intensive energy use of perhaps 225 kilowatt hours per kilogallon. Just to give a sense of the relative costs of thermal equipment reference to reverse osmosis processing. Now, areas of research and development, in talking with various companies, they seem to be certainly addressing cost issues, energy requirements. Many of them are linking ZLD processing with renewable sources of energy, linking processing with the use of waste heat. And again, some of the newer companies are looking at complete smaller treatment systems that involve addressing longer-term issues and let's say, finding a complete solution to the wastewater treatment problem. And finally, in summary, there are many drivers pushing increased use of ZLD. There are many applications, many new applications. There are challenges for predicting performance and cost. There are much research being undertaken. And there's an important role to play with the major manufacturers and these smaller companies to address issues pushing towards sustainability and resource management. So that's the end of this part of the presentation.
Thanks very much, Michael. Do you want to pass me the ball? And we actually have a poll for the audience to participate based on some of those options that Dr. Mickley was just mentioning there. We'd love to hear what the audience think in terms of where do you think the most promising areas for research in zero liquid discharge is going to be, linking with renewable sources of energy, using waste heat, selective recovery of commodity grade salts, or some other area of research. So feel free to use that polling box that should have popped up just now and submit the answer, and we'll review it in the question and answer period. Next up, we will have Daniel Borkland with Aquatech speaking. Dan is he's a chemical engineer with over 25 years of process engineering experience and 16 years of experience in the design of evaporation systems. As the Director of Industrial Concentration for Aquatech, Dan supervises a team of engineers that specialize in evaporation systems used in a variety of applications, such as produced water, shale gas and coal seam gas applications, as well as zero liquid discharge systems for power plants, such as flue gas desulfurization, IGCC, and others. Dan's going to be giving us an overview of some of the industries and markets where zero liquid discharge is currently being used. So with that, I'm going to hand things over to Dan, and he can kick off his presentation.
All right, great. Thank you. Thank you, Michael, for, I thought you gave a really good introduction and explanation of the drivers of the industry. Obviously, you've got a lot of experience in this area, so I wanted to compliment you on your presentation. Getting on with my presentation, I'll be covering markets for ZLD, some of the ZLD success factors as we see them, a few typical plant ZLD configurations, a focus on FGD treatment briefly, and then was mentioned at the end of Michael's presentation, some of the issues with salt recovery for beneficial reuse. Some of the market sectors that we see, ZLD pretty much grew out of the power market and was developed around treatment originally of cooling tower blowdown wastewater. Power plants use large amounts of water, and the cooling towers cycle up in concentration, and then that blowdown, if they do not have a discharge permit, then a ZLD plant is in some cases installed to recycle water, and what leaves the plant is a solid stream. More recent, there's been in recent history, there's been more and more applications for flue gas desulfurization blowdown water treatment, and over the years with gasification technology, there's been a limited number of IGCC plants and other types of gasification facilities that have come on board. The cooling tower blowdown industry, that wastewater is somewhat that water is pretty well known, and the major suppliers pretty much understand that water is characterized by high hardness, high levels of sulfate, and silica levels that where the saturation level gets exceeded in the evaporation equipment. So they've developed processes to deal with that. With the FGD, I'll cover that in a little bit more detail later. The gasification wastewater itself has widely varying chemistries, and it's linked to the type of coal that's used, the type of makeup water that's used, and is highly dependent upon the gasification technology. So it's very difficult to categorize gasification wastewater. You really need to know what type of gasification technology is being applied, and to get a prediction on the blowdown that has to be treated from the gasification supplier. And oil and gas is another growing market for ZLD. I'd say right now in the area of steam flood, which is growing in the Middle East, and in the area of ZLD, which is predominantly in the oil sands in Canada. Those wastewaters are a bit different. If you look at the Middle East, the waters are very higher in TDS. Normally you see chemistries, produced water 8,000, 10,000 ppm TDS with very high levels of hardness and high levels of silica, high levels of varying levels of sulfates, and much different from the ZLD water in Canada, where the produced water there is generally low levels of hardness and also fairly low levels of sulfate, but high levels of silica, and in both cases high levels of sodium chloride. So the ZLD systems have to deal with those. And then you have shale gas and coal seam gas. Coal seam gas is characterized by very high levels of sodium chloride and carbonates, with varying levels of hardness and other divalent ions that have to be dealt with. Whereas in shale gas is somewhat similar. high TDS, and the thing about shale gas, or we're receiving either the flowback water from a frac, or which occurs over the early project cycle on a frac, or if you're talking about the produced water, which comes over the life cycle of a well. You see the TDS of that produced water starts out at a lower level, maybe 20, 30,000 ppm, and after a few years can grow as high as 200,000 ppm, and sometimes higher than that. So you can see that in the world of ZLD, it's difficult to characterize a typical wastewater. It really depends on the market and the source of the water itself. Moving along, there's other, in addition to IGCC, which is integrated gasification combined cycle, there's gasification processes where the companies are converting coal to chemicals, or they might be using biomass as a feedstock, or municipal waste, and also some other feedstocks for those gasification processes. And the wastewater coming out of these processes is widely variable again. So again, we have to have a reasonable estimate of what those chemistries are, and based on our experience, we design the processes to deal with them. I'll be talking about the chemistry aspects of things in some subsequent slides. And also, we're seeing an emerging market in petrochemicals area in the Middle East, in North Africa. We're seeing markets develop for ZLD, where they are from regulatory pressures. They're being required to reduce the salinity of the water that's being discharged to their surface waters. So there's a market that's developing in that area. And as well, there's opportunities for zero liquid discharge in mining. As far as success factors for a ZLD system, it is very important to go to a supplier with relevant experience. As Michael had explained, that it really is a technology where the intellectual property, or the experience of the supplier is very important. There's generally design guidelines are not available from textbooks, journals, and you're not going to find it on Wikipedia. It's very important to have an understanding of the wastewater chemistry, and so we start with where it's coming from, and in many instances we have experience with whatever industry it's coming from, but it's best to have a good design basis for the chemistry to start with, and then also to look at some of the some ranges on the chemical constituents, so that we have a conservative design. Metallurgy in ZLD systems plays a very important role, and it's important, for the end users for us to optimize the capex, and the capex is directly related to the type of metallurgy that we're using. So, in one extreme, you can go to the very highest level of metallurgies, but that comes with a capital penalty. So we're normally trying to optimize capex, and at the same time not sacrifice on corrosion resistance. So again, experience plays a large role in dealing with these water chemistries. And understanding the operating parameters of the system, pH, concentration factors, whether the wastewater has tendencies of foams. Important to understand those things, and very important to include a conservative design margin. It's one of the things that we face as ZLD system suppliers is that the equipment that we provide has to perform over a large variability in chemistry. It's not like a boiler where there's normally a very tight window on the chemistry requirements of the water that's being fed to it, and everybody understands that. The ZLD system is at the end of the pipe, and everything in the plant that's washing into the drains eventually ends up at the ZLD plant. So we need to be very conservative in the design. And once things are properly designed, in many cases, the operating issues can be handled. But starting with the wastewater chemistry is key. Prior experience with similar water chemistry is very important. Sometimes where experience is lacking, and if the water is available, we can learn a lot through a benchtop study. We can take it into a laboratory, do boil-ups on it, and learn how the water is going, and predict how the water is going to react in our evaporation equipment. We also use, as Michael had mentioned previously, we use internal proprietary software for computer modeling, and as well as third-party software such as OLI, which many of you may be using. And if there is water available, and if considered early enough in the project schedule, pilot studies can be done. In many cases, because there is experience already existing, the pilot studies may be unnecessary.
Dan, just to let you know, you're at 10 minutes. You might have to go a bit faster, but we'll run out of question and answer time.
Some of the chemical constituents. Some of the things that we deal with in the chemistry is the calcium. It's a very sparingly soluble salt, and normally we're dealing with calcium sulfate precipitation in the vertical tube falling film evaporators, which Bill will get into in more detail. And these brine concentrators are designed to manage the scaling of these sparingly soluble salts, as well as silica. We also deal with highly soluble species such as sodium chloride, calcium chloride, magnesium chloride, and we're concerned in the ZLD system as these things concentrate up, how they contribute to the boiling point elevation, which leads to higher and higher head requirements out of the vapor compressors, as well as how they affect the metallurgy. Sodium-based salts are generally very highly soluble, and they normally represent the bulk of the solution. We're normally using the forced circulation crystallizers then to precipitate out the sodium-based salts, such as sodium chloride and sodium sulfate, and we handle the bulk crystallization of those salts in the crystallizers. I'm going to pass through this one. Other constituents we're concerned with is we have to deal with silica, ammonia, and boron when we're dealing with, say, coal gasification or FGD. And Bill's going to talk about falling film brine concentrators, which are both seated and non-seated forced circulation crystallizer evaporators. And there's energy supply alternatives. We can do mechanical vapor compression or steam-driven evaporators. Some of the typical configurations, very traditionally, you'd have a brine concentrator, which would blow down to a crystallizer, and then some sort of solid dewatering device, whether it be a centrifuge or a belt filter press, and eventually dry solids. And these are some photographs of some typical systems. And there's some options to that. You could have if you have the ability to have an evaporation pond, you can cut down on your CapEx and OpEx by blowing down directly from the brine concentrator to the evaporation pond and eliminate the crystallizer and the solids dewatering. Or if you could put in a smaller evaporation pond and blow down directly to an evaporation pond. As another option, you can reduce the size of the thermal equipment by installing some sort of an RO process. And we've got a number of years of experience with the technology with a high efficiency RO process where we get high recovery out of the RO. We reduce the size of the brine concentrator and crystallizer to help optimize the system. And in a lot of instances, we can eliminate the brine concentrator altogether and go directly to the crystallizer from the RO process. And in that process is included more traditional water treatment equipment, clarifiers, ion exchange, the RO systems, and then finally a crystallizer. As we look at FGD purge treatment, there's a number of options for that. Traditionally, FGD blowdown has been treated by biological and processes and then discharged. And where discharge is not available, then ZLD processes come into play, where we utilize an evaporator, and we can either then take blowdown directly and mix with fly ash in some instances. There could be a spray dryer to achieve ZLD, an evaporation pond, or the dish goes full ZLD with the addition of a crystallizer and dewatering equipment. Typical FGD purge wastewater chemistry is characterized very high in sulfates and hardness and chlorides and TDS. If we look at a typical configuration of what's been operating for several years, we take the FGD purge wastewater where it's very high in calcium chloride, and we bring it into a lime neutralization clarifier along with sulfide. We're neutralizing the wastewater and also precipitating heavy metals, and then add soda ash, which is precipitating calcium carbonate, and as a result you end up with a sodium chloride or a sodium-based chemistry to the evaporator crystallizer, which operates now more traditionally in dewatering equipment. And the process looks something like this. You have the clarifiers, the brine concentrator, crystallizer, belt filter press for dewatering of the salt cake, and then the salt cake for disposal. And finally, when you look at zero liquid discharge, there is a push for beneficial reuse of these solids, and in that case, the crystallizer gets a little bit. There's some additional equipment that has to be added in. The salt cake coming from a traditional ZLD crystallizer, we would call it a mixed salt crystallizer. So in this case, we would need to modify the crystallizers and design it specifically for producing a pure salt cake to meet a particular spec, which would include the introduction of salt washing, solid centrifuges with washing, as well as salt drying, and then storage stations. So in that case, there's some additional equipment that would need to be added in, and so the market for that salt for beneficial reuse would need to consider those additional costs as well. So Tyler, I'll pass it back to you.
Thanks very much, Dan. That was a really interesting look at some of the key markets for zero liquid discharge technologies, and some really good examples of how that configurations kind of look and what some of the constituents of those wastewater elements are. Next up, we have Bill Shaw with HBD, a Veolia Water Solutions technology company. Bill has he's a chemical engineer, a degree from Cornell University and a master's from the University of Wisconsin-Madison. He's got 35 years of experience in process design for evaporators and crystallizers in a variety of industries, including chemical, pulp and paper, food and bev. And in the power generation industry, he's designed zero liquid discharge systems for wastewater from many of the things we were just talking about: cooling towers, FGD scrubbers, gray water from coal and petcoke gasification plants. And he's published several articles in journals such as Power, Chemical Engineering, Industrial Water World, and Ultra Pure Water. And Bill's going to give us an overview of the different technologies, what's used for different applications, and how those systems look. So I'll hand it over to Bill. You can unmute yourself, Bill, whenever you're ready, and start the presentation.
There we are. Good morning, everyone. Bill Shaw from HPD, Veolia Water. HPD is the evaporation and crystallization group within Veolia Water. We've been around for a long time, and we have lots and lots of installations all over the world. So I hope we can give you some insight into the technology behind these creatures called evaporators and crystallizers. As the previous presenters have indicated, ZLD has some typical objectives. Of course, every situation is different, but typically we're trying to eliminate liquid discharges from plants. And of course, when we design a ZLD system, we want to accommodate lowest capital and operating costs and minimize the manpower requirement and make the simplest and most robust system possible. How is ZLD achieved? Again, as the previous presenters have indicated, typically there's a pretreatment step involved which conditions the wastewater so that it can be put into, say, a primary volume reduction using membranes, reverse osmosis, ultrafiltration, nanofiltration, what have you, and then an intermediate volume reduction, usually done in an evaporator, and a final concentration to solids, which may be done, as the previous presenters have shown, in evaporation ponds, spray dryers, or a thermal crystallizer. This will give you a little bit of an idea. I'm not going to spend a lot of time on this, but as the previous presenters have shown, RO has an upper limit of as to how high you can concentrate in an RO. It's generally about 4 to 6%. Evaporators, maybe you can get up to 20%, and of course crystallizers we can get nearly to dryness. Notice also that as most of the water removal is done in the RO and evaporator steps, and the crystallizer does fairly minimal water recovery, but that's not its purpose. Its purpose is to get us to dryness. Again, the economics, this will just give you a relative idea. Membrane systems are generally made of plastic, and they concentrate the brine up to a fairly low concentration, as I said, about 4, 5, 6%. Evaporators tend to be more expensive because they go to a higher concentration and also have more metallurgy requirements. And of course, crystallizers going to dryness have the highest cost of all. But they do the least amount of water removal. So even though the cost is quite high, the evaporation rate is quite low. I think these numbers are in line with what Mike presented earlier. The energy requirements for RO and the capital costs are relatively low compared to evaporators, and of course compared to crystallizers. What are the things we worry about? Again, in ROs, evaporators, crystallizers, we worry about scaling and fouling. We worry about organics carrying over into the distillate or other volatile components. We worry about osmotic pressure and boiling point rise because that determines the amount of energy we have to put in. And then we worry about things like foaming and how difficult it is to separate the solids out. What's a basic evaporator? It's basically a heat transfer surface on one side, which we condense steam and transfer heat. Oops, sorry, went the wrong way. Transfer heat across the heat transfer surface to take a feed stream, boil it, produce water vapor and a concentrate. The water vapor gets condensed by using cooling water. So we have a product condensate or a distillate stream. We have the concentrate, and we have the steam condensate as final products from the basic evaporator. There's lots of different types of evaporators. This is a starter list. There's lots of other kinds besides this, but these are the major ones that are used. This gives you some idea of the configuration. We'll talk about two. The two on the left, fouling film and forced circulation, are most often used with ZLD. Rising film and natural circulation are generally used for production units in non-scaling applications. So you'll see those in pulp mills and caustic plants. The fouling film evaporator is basically a heat exchanger that's welded onto a vapor body. The heat exchanger is up here at the top. It extends into the vapor body. The vapor body is a place in which the evaporated water vapor is separated from the brine. The brine collects in the bottom of the this vapor body, which is sometimes also called a sump. It gets recirculated back to the top of the evaporator. Distillate is produced in the heating bundle, tube bundle, and the product is taken out. There's another arrangement for falling film evaporators, which is generally used for non-scaling applications, non-seeded applications. This is a so-called collinear falling film, in which the vapor body is separated from the evaporator tube bundle, basically. And this has some advantages in non-scaling applications, but typically for scaling applications, it's not as favorable. For circulation, evaporators are generally used for the crystallizing duty in ZLD systems. The heat exchanger can be oriented either vertically or horizontally. You'll notice, though, that the heat exchanger is located below the level of liquid in the vapor body, so that the heat exchanger is flooded in a forced circulation type unit. No evaporation occurs inside this heat exchanger. It's just sensible heat that's transferred. All the evaporation occurs as a flash in the vapor body. As Dan alluded to, sometimes we want to make large crystals and pure crystals, so then we can do some things to add and modify the crystallizer. We can add a draft tube, which helps us to make large crystals and more pure crystals. We can add elutriation legs, which are used to wash the crystals, and so forth. But that's typically not a concern with wastewater, because typically for most ZLD systems, the solids go to a landfill. This is a so-called brine concentrator system. It consists of the basic evaporator, but it has a couple of components. Besides that, there's a tank to add some chemicals, to adjust the pH, and to make sure that we have all of the components necessary to remove any dissolved gases, which is done in the deaerator. There's usually a compression device, a compressor, because these are typically MVR systems or mechanical vapor recompression systems. And then there's a seeding system or a seed recycle system, which we'll talk about in a minute, to help us control scaling in this brine concentrator system. The heart of the brine concentrator is the falling film evaporator. Again, it's a tube bundle with a distribution device located at the top. There's a recirculation line and a recirculation pump, which bring the brine to the top of the heat exchanger, where it falls down the tubes. Evaporation occurs within the tubes because water vapor is condensing on the outside of the tubes. The distillate is collected and pumped out of the system. The water vapor goes to the compressor. Again, that's a typical falling film. This is what it looks like at the top. A typical brine distribution device consisting of perforated plates. It's a dual perforated plate. At the bottom, you can see the vapor body. This, again, there's a level of liquid which is maintained in this to provide submergence for the recirculation pump. There's some vapor or entrainment separators to clean up any mist that might come along with the vapor, which is going to the compressor. There's a distillate outlet to collect the distillate water that is produced. What goes on the tube surface is shown here. There is a tube. The brine is distributed uniformly across the tube bundle. In each individual tube, the brine runs down the inside wall of the tube. Heat's transferred across the tube from condensing steam on the outside. The liquid film boils. Water vapor goes down the tube along with the brine. The seeded slurry process is a way to control scaling in the evaporators. Typically, we have low solubility salts like calcium sulfate that are present in the brines that are typically concentrated in brine concentrators. So we use seed crystals of calcium sulfate. The idea is to present, like likes to precipitate on like, so we put a lot of crystals in to the brine that's circulating around. The low solubility salts preferentially precipitate on the seed crystals rather than on the heat transfer surface. That's why it's important to have a large sump in the brine concentrator, because that's where supersaturation is relieved and the crystals grow. If you have a small sump, then typically the crystals will grow on the heat transfer tubes. The brine crystallizer, we showed that before, is a forced circulation unit. This is a typical steam-driven, single-effect forced circulation brine crystallizer. Here's the forced circulation evaporator. There's a condenser to condense the final vapor. That's our distillate water. There's a solid separation device, which I'll show you a couple different examples of in a minute, either centrifuges or filters. And then there's a tank to collect mother liquor and feed and put that back into the crystallizer. So you can see the only output from the system is the distillate water, which is recovered, which hopefully we can recycle, and solids, which go to either disposal or reuse. Again, the forced circulation evaporator works on the basis it's a flashing type evaporator. The brine, the heat transfer surface is flooded. It's always located below the level of liquid in the vapor body, so only sensible heat is transferred in the heat exchanger, and that heat flashes into vapor when the hotter liquid gets to the vapor body. Vapors go through a mist eliminator and exit and go to either to a condenser or a compressor. Again,
Bill, you're at 10 minutes.
Okay, all right. So our forced circulation, again, we're talking flooded tubes, high velocity to get good heat transfer. There's many different arrangements to put energy into the system. We can have the single effect, as we talked about before, using steam and a condenser. We can multiple effect evaporators, where we use the steam from one effect to do evaporation in a second and third effect. Each effect is at a lower pressure than the one before. We can use mechanical compression, which is sort of an open cycle heat pump. Take the vapor and compress it and reuse it as heating steam. We could use a thermal compressor, which is using high pressure steam to entrain the lower pressure steam out of the vapor body and recycle it back to the heater. We can use a direct heat pump, which uses an intermediate refrigerant liquid to transfer heat to the brine that's being evaporated. Solid separation devices, belt pressure filters, centrifuges, spray dryers, those are just some pictures of them. I wanted to talk really quickly about the latest and greatest ZLD process, which is the cold process. It specifically addresses the crystallization of high solubility salts. It's done at low temperature and deep vacuum. The beauty of the cold process is it eliminates a couple of steps in the traditional ZLD sequence, the pretreatment step and the drying step. So all those softeners that you saw in Dan's presentation can be eliminated, as well as the drying step at the very end. What does that mean? That means we don't have chemicals for pretreatment. We wind up with less solids to dispose of. It's a simpler system. Even though the CapEx and the energy requirements are similar to the conventional process, the OpEx is much lower because we have less chemicals and solids. High solubility salts, again, some examples were given earlier, calcium chloride, magnesium chloride, ammonium chloride, any kind of nitrate salt, salts of organic acids like formates and acetates. All of these are examples of high solubility salts. Where do we see them? FGD scrubber wastewater from wet limestone scrubbers is rich in calcium and mag chlorides. Coal gasification wastewater, ammonium chloride and formic acid, both very soluble. Frac flowback and produced water, again, the calcium chloride and the magnesium chloride. Here's just a really quick comparison of 350 gallon a minute ZLD systems, one using softening plus evaporator plus crystallizer for FGD, sort of the system that Dan showed you before in Italy. This compares to a same capacity system using the cold crystallizer. You can see that the system requiring softening uses a lot of chemicals and generates a lot of solids for disposal. Even though the energy requirements are higher for the cold system, the bottom line is much, much less because we eliminate those chemicals and so forth. This is a conventional crystallizer. We've seen this before. This is a cold crystallizer. It's just a vacuum version of the conventional crystallizer, a deep vacuum version, which means that often we need to have chilled water used for the condenser. That's why we have generally a higher energy requirement. So we have a deep vacuum crystallizer, very good for high soluble salts like FGD wastewater, like IGCC wastewater, landfill leachate. The low temperature lowers the solubility of the salts so they come out of solution easier. We could use steam and chilled water, or we could use that refrigerant heat pump I showed you earlier. And this is a patented process for FGD and IGCC blowdown, shale gas produced water, and landfill leachate. I'll just show you a couple of quick examples. Here's a cold crystallizer system for an IGCC power plant here in the U.S. that's due to start up this year. There's two cold crystallizers actually in this system. There's a ZLD system for landfill leachate, which is this particular one's in Europe. Here's an FGD scrubber blowdown. Okay, and I'm just about done here.
Yeah.
Cooling tower blowdown, soda ash, some coal mine waters, ZLD. This is the largest MVR crystallizer in the world, and this is the largest ZLD system in the world as a petrochemical plant in the Middle East. So, thanks again. Sorry to take so long, and we will talk to you soon, hopefully.
Thanks very much, Bill. That was excellent. You can clearly see after Dan's presentation where we saw how complex each of the different wastewaters are, that there's a lot of different systems that are being used to address these different complex waste streams. So we're going to enter the question and answer period now. Thank you again to Mike, Dan, and Bill for excellent presentations. Again, those slides are going to be sent out to everyone following the webinar, so you can look forward to reviewing all those slides in detail. We've been getting questions in, and I'll direct those to the panelists who you can unmute yourself when you guys want to chime in. I guess for a starting one here, we have a question about inland desalination, maybe for brackish groundwater. We've talked a lot about primarily industrial applications. I haven't really touched on sort of the municipal side. So maybe each of the panelists could tell us a little bit about what they're seeing with, say, municipal drinking water or just general desalination plants and zero liquid discharge. Maybe Mike wants to start off, since I know one of those recent reports looked at ZLD for water utilities.
Okay, am I on now?
Yep.
Okay. Indeed, there's a growing interest in applying high recovery processes, and including ZLD, to the municipal drinking water industry. However, to date, there's only been one ZLD process implemented in Tracy, California, and it indeed uses thermal equipment. The problem of penetrating into the municipal market is one of cost. The economics surrounding the municipal industry are much different than those from most industries. But because of the same concerns with finding disposal options and those becoming more difficult to find a feasible one, there are increasingly more questions posed and more feasibility studies done with the application of ZLD. But again, it will probably happen very slowly, primarily due to the higher costs associated with ZLD.
Thanks, Mike. Bill and Dan, do you have any thoughts on this area? I see Dan's still muted. Oh, there you go.
There is interest in the area, specifically in inland desalination. But I think some of the problems that they face are, well, what they'd like to do is recover salts and reuse them. But I think the major challenge right now is finding the markets for the products that would result. I think that technology exists. Other options for disposal, I guess, that would be available right now would be it would be the ZLD directly, evaporation ponds if they're available. You could reduce the size of the pond, use an evaporator up front, or deep well injection is a common disposal method. And normally there's water is recycled from the brine prior to disposal through various methods that were discussed in the presentations.
Thanks, Dan. How about you, Bill?
I have nothing further to add than what the others have said. Thanks.
Great. Well, we had another question come in about the materials used to make thermal evaporators and crystallizers, and just wondering what your thoughts are on some of the alternative materials. The question was specifically talking about FRP, I guess assuming fiber reinforced polymer. Have any of the panelists seen anything like that? Or are you working on things like that?
This is Dan. I can answer that, or I'll try and answer that. The environment of the brine, due to the brine, really the temperatures, there is some role for materials like FRP to play, but generally in the process, evaporator vessels themselves or the crystallizer vessels themselves, we tend to want to, in order to give a 20 to 30 year service life, we stay with the alloys. FRP, while a good material, I don't think could in all instances get a 20 to 30 year life. We do use and have used FRP in some of the piping systems. We've also used some rubber-lined carbon steel in certain circumstances, and normally some of those circumstances we're doing that in vacuum conditions. So there is we're always trying to find capital optimization of capital by using alternative materials, but I think in general we're using high alloys for the main evaporator components from a service life perspective.
Thanks a lot, Dan. Unless Will or Bill or Mike want to chime in there, I might, on the topic of innovating with different materials, bring in some examples of some other systems that I know there's been some research in looking to combine for zero liquid discharge. It'd be great to hear the panelists' thoughts on forward osmosis and membrane distillation and some of these other technologies and how that might be used in the ZLD applications. Maybe if Bill or Dan has any, have either of you seen any examples of that?
I am, I'm quite sure that there'll be more innovation in the area of membrane systems. One of the innovations since for the past 10 plus years was the use of high efficiency reverse osmosis or HERO membrane systems in order to get better than 90% recovery in order to minimize the size of the thermal ZLD system. And I am quite positive that is an area that we are actively in research in, and there'll be innovations going down the road to further innovate on pre-treatment in order to minimize the cost of the thermal system. But eventually, you get to a situation where the scaling constituents of the water can't be avoided. And at some point, you're going to need a thermal system in order to, at the back end of the plant, the object is to minimize that thermal system, and that's where the HERO system has been very successfully employed.
This is Mike. I think the promise of both forward osmosis and membrane distillation is relative to reverse osmosis, and it's to provide higher recoveries, achieve higher degrees of concentration, and not be limited by the osmotic pressures, as is the limitation in membrane systems once the scaling issues have been bypassed. So it may mean that there's more concentration done prior to using the thermal equipment. If once forward osmosis and membrane distillation is more widely proven and entered into the marketplace.
Thanks, Mike. Maybe going forward from this, continuing to talk about innovation, I'd be curious to know where do each of you see the majority of, say, R&D activity? Is it in improving either evaporators or the crystallizers, or is it in doing clever configurations? Is it in these additional improved reverse osmosis, forward osmosis, membrane distillation? Where do you see the majority of sort of R&D activity, and maybe where is the most promising area, do you think, in terms of bringing down the cost for ZLD that might make it become adopted in other markets? Bill, do you want to suggest anything?
I'm having some difficulty here. Can you repeat the question? I can't quite hear what you just said.
Sorry, Bill. I was just asking about what area do you see maybe the most activity with respect to R&D for zero liquid discharge? Is it in improving crystallizers and evaporators, or in the sort of earlier concentration steps such as RO and forward osmosis, those technologies, or in just how systems are configured? Where do you see most of the innovation in R&D?
I think it's all of the above. Certainly the interest is in membrane distillation and forward osmosis as possible steps to improve the inexpensive recovery of water prior to the expensive thermal processes. But there's also R&D going on at the back end. The cold process is a good example of that, where we're trying to sort of move on from the 98% of ZLD systems which are designed for cooling tower blowdown, which, as Dan said, is a pretty well-known item on how to treat it, to some of these newer applications where we've got really highly soluble salts that just don't want to crystallize out in an ordinary atmospheric crystallizer because the solubilities are so high. And so that's where, you know, the interest is in finding ways to get these solids out of solution so that we can have a true ZLD system. And this is where I think a lot of people go wrong. Everybody thinks, well, you know, whatever comes out of the evaporator you can put into a crystallizer. Well, not necessarily so, because the crystallizer, if the salts are mainly highly soluble nitrates or calcium chloride, they aren't going to come out of solution very easily. And the materials of construction will have to be, you know, Hastelloy or better, and the temperatures used to process, if we use atmospheric pressure, are going to be quite high in the 350-degree range. So that's where R&D works to help get those solids out of solution.
Thanks for that, Bill. I have a question coming in here about pending legislation that requires ZLD. I know certainly Mike's done a lot of research in the area. Maybe, Mike, you can tell us a little bit about where ZLD or legislation that might require ZLD is changing or coming into effect.
Well, that's a question I really haven't considered. I'm not aware of any legislation that might force that, other than, of course, there's concern associated with gas shale in terms of the amount of water that's required for processing for the fracking operation. And I think there's a real concern about whether the amount of water needed for that will heavily impact on water resources used for other applications. And I guess I wouldn't be surprised if in various locations there were some mandates for including water recovery, water reuse, recycled water within those operations to minimize the need for outside water. Whether that, how widespread that might be, I do not know. I know that's an issue that's being discussed.
Thanks, Mike. In terms of new and emerging markets, I know Middle East and North Africa was mentioned as being an area where there's sort of a growing market. It'd be great to hear from each of the panelists where they're seeing new markets. I've heard recently that India, with the sort of the wet industries there and the lack of ability for lack of water resources for those industries, creating a lot of opportunity for zero liquid discharge. You know, maybe you could tell us about what other regions seem to be a growing sales area for ZLD technologies. Maybe Dan can chime in first.
Yeah, we see a market emerging, as I said, in Middle East, North Africa area, and then a big market for ZLD because of all the gasification facilities or all the coal in China that's being processed by gasification processes. There's a ZLD market in China that has been developing for several years now. We've provided some systems in that market. And then, markets such as India is another area where ZLD is emerging, but is not quite mature yet. As in some of these markets, what we see is there tends to be a desire to look at ZLD, but then it's an expensive process, and so it doesn't gain traction, or systems are installed that maybe don't, from suppliers that might be local that don't have the experience, and maybe the systems don't have to work so good, and that sometimes happens in some countries. But as things mature, then the systems, and as regulations tighten, then the systems have to work, and that's where a market such as India will eventually go, and there'll be a market for ZLD there as well, and I'm sure there's other areas in that region where something similar will happen. I think ZLD is still in its infancy, and will due to water scarcity issues, regulatory issues, I think those are pretty heavy drivers for projects, for requirements for the end users.
Mm-hmm.
This is Mike. I know in Australia, in terms of coal seam gas, what to do with the water is a major issue, and what has somewhat held up the technology beyond the position the environmental and the government groups have put kind of a hold on things. The technical issue is what to do with the water, and I'm aware of the companies that are involved there are looking very heavily at recovering as much water, minimizing the waste as much as possible, including recovering of salts.
Thanks, Mike. There's a question here from a couple of people about areas of research for ZLD. Just want to bring up that poll that we had done so that the audience can see what the audience think is sort of the most promising areas of research. And while we're looking at that poll as well, one of the areas we'd like to discuss is around the use of basically recovery of salts. I'd love to hear from the panelists as to what we know. There's not a huge market for it right now. Why is it that recovered salts isn't driving this yet? And is there an opportunity for with the water that is recovered of not treating it quite to the high quality standards for drinking water, maybe, but fit for purpose reuse of that water, or maybe treating it to a lower standard? Maybe that would help with the economics. And it looks like here recovery of commodity grade salt is actually what the audience thinks is the most promising area of research. So maybe we can speak about that. Whoever wants to jump in first, feel free.
This is Bill. This is a question I get a lot, and it's a great question because I think it goes to the next level for ZLD, which is sustainability. ZLD has been driven by regulation up till now, and still really is in most markets and in most applications. But there is this desire, if we're going to put in ZLD systems, why don't we try to recover something useful from the brines we try to eliminate here. The real thing that unfortunately is the case with most of these wastewaters and brines where we're looking at ZLD as a technology, is the salts that you recover are generally not worth all that much. They're commodity salts, and there's not a big market for them. The market for them tends to be for things like road salt, which is a seasonal thing, and also is frankly, again, not a very high profit business. So I think that inhibits a lot of it. Actually, in a lot of cases, the water is the most valuable byproduct, and what comes out of the evaporators and crystallizers basically is distilled water. It's actually not good for drinking water because it has no taste. In order to use it for drinking water, you have to remineralize it. So, but it does have lots of uses for reuse in industrial situations, and I think that's where the one of the impetuses, or one of the major impetus will be, is the water recovery itself, not so much the salt recovery.
This is Mike. I know there are. I've been involved in a project in Oman where they import a lot of salt, and so some produced water companies that have a lot of produced water were thinking of recovering salts and at a much lower cost than importing it. So that's one of the drivers for this. In terms of the value of salts, there are some specialty salts. There's a form of calcium carbonate called precipitated calcium carbonate that is quite valuable, pushing up perhaps to $300 a ton, and it's used in high-quality paper. Some of the magnesium hydroxide chemicals are fairly valuable. One of the very general concerns, I guess, about salt production is you need a local market for it, and there may be demands on the purity and the quality of the crystals and so forth. And while there are many research projects showing that indeed you can isolate certain salts, there's been relatively little work done in producing salts of let's say, high quality to meet very specific markets. There may be a concern with saturating local markets. And so I think ultimately, as Bill mentioned, this kind of this push towards sustainability, it's not necessarily with the salts that are directly recovered, but what can we do with those salts to develop value-added products? It would be great if for a magnesium-based water to produce building products. And I know there's some efforts along those lines. Some of the required or the recovered salts can also be used in other processes to, for instance, using some chemicals to actually generate on-site chlorine disinfectants and so forth. So it's not perhaps a direct use of the salts, but using some of the recovered salts to produce a usable, valuable product after an additional number of processing steps.
Right. Tyler, if I have an example of this, if you want to go back to slide 107, we have some installations where we are recovering byproduct. Well, this is sodium carbonate, not calcium carbonate, but again, a very valuable byproduct, which has a value of upwards of $300 a ton. Again, recovered from a wastewater at a mining facility. And that's also the case in the slide 108, which is also a mine water processing facility.
Thanks very much, Bill and Mike, for sharing your thoughts on those topics about recovered salt and the water. Unfortunately, we've now reached our time limit, and we're going to have to bring the webinar to a close. Thank you so much to Bill, Mike, and Dan for outstanding presentations covering the very complex issue of zero liquid discharge technologies and all the different markets in which those technologies can be applied. I'm sorry we didn't get to everyone's questions, but we will have a record of them, and we'll seek to get replies to you in the next week. Thank you again for attending this webinar, and if you're interested, the next Blue Tech webinar will be on the water and wastewater issues in the oil sands, and if you want to stay up to speed with all the webinars that Blue Tech Research puts on, feel free to join our mailing list at bluetechresearch.com. Thank you very much for attending, and we hope to speak to you again soon.